welcome everybody. I think most of you know me, but let me introduce just quickly myself. I'm Samson Shatashvili. I'm University Professor of Natural Philosophy in this university and also Director of Hamilton Mathematics Institute. One of the reasons we are meeting today is because it's 20 years anniversary of Hamilton Mathematics Institute and 220 years of William Rowan Hamilton, who obviously is something that Trinity is proud of. From age 15 to his death, he was working in this university, so this is a main reason. I just want to kick off this small conference to say a few words about each speaker when I introduce them. And our first speaker is a very distinguished mathematician. In my view, very few will match Maxim Kontsevich in his achievements on various fields of mathematics. Some of them even I can understand. Maxim is from Institut des Études Scientifiques from near Paris, which is in Bourg-sur-Yvette. He has won every prize I know, except Nobel Prize. Abel Prize, you have to get older, sorry.
Okay.
You have to get older. One year he even won 3 great prizes. I will not give a monetary value, but substantial. Now, Maxim is also one of the 4 or 5 members of Hamilton Mathematics Institute board. Other members are here. I will talk about them later. Actually, next speaker is also a member of the board. And we are happy he agreed to come, because Maxim, believe me or not, is a very busy person and is one of those few mathematicians that no matter what happens, he continues producing great mathematics. His talk today is called Resurgence in Quantum Mechanics, and you will see almost, in my view, if I would be giving talk with this title, Hamilton would be everywhere, okay, in his talk, I hope. Please, Maxim.
Okay, thank you very much, and I'm honored to be the first speaker on this conference, which is 220 years of Hamilton and 20 years of the Institute. So I'll speak about very, very basic stuff, which at the beginning, which everybody who learned a little bit of physics knows. It's about Hamiltonian and Lagrangian formalism. In fact, it's a very unclear story. It looks that maybe Lagrange was first wrote Hamilton equations before Hamilton, and maybe was, so it's a complicated story. I will leave to Nigel Hitchin discussion of this British-French rivalry. There was a least action principle, which observes that all equations in physics, in classical physics, one can use for least action principle. It's actually not least extreme action principle. It's not minimum or maximum, but just the point when derivative is 0. And the action is given by integral of Lagrangian. So in mechanics, you suppose have some mechanical system, you get what's called configuration space. Usually it's Euclidean space. It's positions of some collection of particles, let's say in R3 or something like this. And you denote collectively this by letter Q. And then you consider particles depending on time, so Q of t, and you fix some interval of time from t0 to t1. And you integrate some quantity which depends on positions, velocities, derivative with respect to time, q dot, and also it could be time-dependent Lagrangian. So it's like external force could depend on time. So you write some action functional, this integral of some Lagrangian, and you're looking on critical points, not minima in fact, but just critical points, and variation derivative is 0, and it's a famous Euler-Lagrange equation, which you can translate by variation calculus to usual differential equation for the position of particles. And this will be a second-order equation. If you analyze this thing. It will be second equations of second order in time for position of particles. And then there is a Hamiltonian formulation. So you define function of, again, three groups of variables. You get positions. Now you get conjugate variables, which are not velocities, called momenta. It's denoted by collectively by p, the same number of these variables as coordinates, and again, maybe depending on time. And for each value of time, you consider Legendre transform of this Lagrangian as function in velocities, in q dot. Yeah, this makes sense if function is convex in q dot. It's really convex, then you can make kind of this will be unique supremum, and you get well-defined function, maybe in some domain in dual space. And miraculously, the equation of motion, which second-order equations in original configuration space, became in this doubled variables equations of first order and very, very kind of symmetric. You see this kind of no difference between P and Q, except of signs. So you have you take derivative. You take for each value of time t, you take derivative of Hamiltonian with respect to p, and it will be the speed of q, and vice versa, up with minus signs with q and p. So to this day we say that we have symplectic manifold, and you get family of Hamiltonians depending on time, and we have Hamiltonian non-autonomous Hamiltonian flow. Okay. Yeah. So so the trajectory of Hamiltonian flows in the space of double dimensions called phase space with coordinates p and q, and in invariant terms you get close to form, non-degenerate to form, dp wedge dq. It's called symplectic structure. And these trajectories in the phase space are solutions of another Euler Lagrange equation, because you map now time axis to double space, and it turns out again will be a solution of some variation principles. And the new Lagrangian, it's now for two functions of t, p and q, a priori independent, and you integrate p times some of indices pi times qi dot and minus the Hamiltonian. Yeah, so you started with Lagrangian formalism, you got Hamiltonian formalism, now you get again Lagrangian formalism and double number of variables. But you cannot repeat this procedure because this Lagrangian is in derivatives. You look in derivatives, it's a linear function. It's only linear, it doesn't depend on p dot at all, it depends on the q dot. It's linear function, and so it's very degenerate Lagrangian. You cannot make a Legendre transform of it, yeah. But it's still kind of formally a variation principle. It's called first-order formalism. So we kind of reformulated back Hamiltonian viewpoint to Lagrangian, but with kind of very degenerate Lagrangian. And this has some invariant meaning in symplectic manifold. If you don't choose coordinates, you look abstractly about manifold with closed non-degenerate to form omega. Oh, sorry, I forgot dot here. So the integral of p times q dot dt can be understood the integral of your curve of one form p dq. And what is form p dq? It's kind of primitive of closed form omega. Its derivative, its exterior derivative is form omega. And what are boundary conditions? And boundary conditions for this degenerate Lagrangians are the following. In the original story, we fix a value of trajectory at endpoints for t0 and t1, but here we don't fix them entirely. We say that for time t0, it should lie in some Lagrangian submanifold, and T1 is another value in time T1 this point should lie in another Lagrangian submanifold. What is Lagrangian submanifold? It's submanifold of half dimension of M, so you have only half of constraints, on which this two form omega vanishes. Yeah, so the word Lagrangian here it's kind of used in two senses. It's Lagrangian for writing action functional and subvarieties in symplectic manifolds. Yeah, in fact, Lagrangian submanifolds are the most important. Are more important than points of symplectic models. So it's kind of replacement of points, and so you see that in the symplectic geometry, which is use both names, Hamiltonians, like functions generating flows preserving symplectic forms, and Lagrangians, not Lagrangian in the sense of actional functions, but these submanifolds where paths can start and end. Okay, so what is example from quantum mechanics? It's quantum mechanics? Classical mechanics, yes, sorry. Sorry for some misprint. Yeah, so you consider particle of mass 1. Usually physicists, when write formula, they put m as a mass. Yeah, but a mathematician, I want to avoid this kind of unnecessary letter. In some potential, which could be polynomial, could be quadratic, like sum of squares, or maybe some quartic potential. It should be some function which goes to plus infinity. So you imagine particle moving in some external field, which is given by the potential, and in usual Euler-Lagrange formulation, you get second-order equation of motions that the second derivative with time it will be minus gradient of potential at this point. And here there's no dependence on time, so both Lagrangian and Hamiltonian are time independent, and Lagrangian is q dot square divided over 2 minus potential. So you see this Lagrangian, it's not really positive. In q dot is positive, and in q it's negative. Yeah, so it's for the what's called least action functional, it's a bit misleading term because you don't really minimize. It's like even if the potential is quadratic, you extremize quadratic form which is indefinite. And Hamiltonian here it's literally positive. It's p square plus potential, and also and we also have this phase space Lagrangian in two variables, which is p q dot minus Hamiltonian. Yeah, what are boundary conditions in this example? In example of particle and potential, at endpoints, q coordinate should be some specific point of your manifold. It's what was kind of usual boundary conditions in original formulation. We move from one, may try to draw geodesic from one point to another point, roughly. But here, because we add variable p, we have a very simple half space, which is abstractly fiber of the cotangent bundle, because q can consider coordinate manifolds, and p will be not tangent bundle but cotangent bundle, and you have, the conditions you stay in these fibers. And still repeating this invariance under time shifts. In this case, is invariant under time shifts, and then we can try to see the following. So we have some theory which we map some one-dimensional manifold interval or piece of line, and invariance of time shifts means that it's invariant under shifts of R. And what are shifts of R? Are isometries in one dimension. So it's a bit kind of funny point. One can see that you want to theory in one-dimensional space-time, which is only time, invariant under isometries, which are only time shifts. So this quantum mechanics, it's kind of like baby version of it's called QC, of field theory in Minkowski space-time. But it's one-dimensional, it's kind of one-dimensional field theory. And later, you'll see that what is really important to have another class of examples which do not directly come from quantum mechanics when Hamiltonian is zero. And when Hamiltonian is zero, it's not only invariant under shift of time, it's just literally zero. Then this action functional is invariant under diffeomorphism of time reparameterization. Because you just integrate one form on a curve, it doesn't depend how you parameterize this one curve. And this theory is topological. So it's kind of funny point of view. You see that it's kind of famous subject in modern theoretical physics. When you quantize these things, consider topological quantum field theories. And I think that appears already in quantum mechanics when Hamiltonian is zero, but to get something interesting, you should take not the stupid fibers of cotangent bundle, but some kind of curved Lagrangian subvarieties. And if you get curved Lagrangian subvarieties, they typically, because they have middle dimension, intersect at isolated points. And the solution of equation of motions are very uninteresting in this case. When you get this first order formalism, take zero Hamiltonian and take two boundary conditions, and you write equation of motions, you see immediately that the equation of motions force this map from time interval to your symplectic manifold to be constant map. But because both endpoints should belong to Lagrange manifold, should be constant map to intersection points. And usually they intersect like finitely many points, you get just this finitely many very uninteresting trajectories. Oops. Okay. So now I go, so I was a bit wrong with the title previous page. Now I go really to quantum mechanics. What is quantum mechanics? You go to Lagrangians in original setup when it depends on Q dot and time. So you get a functional space of trajectories in configuration space. And now we take exponent of I square root of -1 divided by h bar, which is called Planck constant, and times the action. You get a function on the space of trajectories with values in complex numbers with absolute value 1. And you integrate, you imagine the space of trajectories some infinite dimensional manifold. And if you make, it's like infinite dimensional vector space. And it has coordinates like value of qi at all point values of time between t0 and t1. And you kind of, in a sense, take Lebesgue measure in this infinite space. So the Feynman proposed the picture that you should interpret quantum mechanics as a calculation of such integral, of oscillating with phase equal 1 complex valued function of some infinite dimensional manifold. It was for the original action functionals, like kinetic energy plus minus potential energy. And formally, one can identify with even more singular path integral in the first order formalism. Now consider two functions of t, coordinate and momenta depending on t, and you get this very degenerate Lagrangian here. So kind of by hand waving, one says that this one integral is equal to another integral. Maybe we should introduce some Jacobian here, but in first approximation, they should be the same. And the first kind of original Feynman path integrals makes little sense, and its real version when you replace I by -1 of h bar, so you take exponent minus some expression which is not really positive definite, but at least kinetic energy is forces to be close to be positive than negative. So you hope to get kind of like convergent integral of real exponent and to get some real number. In fine path integrals, you get not real number in general, complex numbers, because no reasons for these things to be real. And this thing, there is some mathematical series, this actual measure and there is actual theory of integration, which makes perfect sense in this case for particle potential. It's called theory of Brownian motion. You consider Brownian motion's probability measure on space of paths. Paths are very singular, where the action doesn't make sense for the path because paths are very chaotic and integral square derivative is infinite, but somehow these things can be considered as a definition of this integral. And and this is called Feynman-Kass formulas, that this things is given by Brownian motion, it's called heat kernel, and there's a very rigorous science. I have to say that if one consider this quantum mechanics one-dimensional fields, quantum field theory, one can follow the same path in other dimensions. And again, it's kind of much easier to study real integrals than oscillating integral. And for real integrals, there is a huge domain of science how to construct, how to define random fields, analogs of Brownian motion in many variables, and in dimension 2 and 3, it was a successful story. And by weak rotation, was so-called weak rotation, when I construct this actual measure and rotate time to it corresponds to actual physics in imaginary time, and by analytic continuation, one can get quantities for oscillating integrals. But the oscillating integrals, there's really no, to my knowledge, actual theory. Because if you have integral, you can try to integrate over subdomain, not over whole space. It's like measure theory. You get not just one integral of the whole space of trajectories, but maybe of some domains. And for this oscillating thing, there's no such notion at all. Only the total number, the total value of the integral can be defined, but through some kind of a postulate. You have another viewpoint on quantum mechanics through Hilbert spaces and quantum Hamiltonian, and then from this you can define what is the value of the integral, but not really starting from the integral. Okay. Yeah, so now there's a funny game. Planck constant is called constant, but I want to consider it to be not constant. It's a parameter which goes to 0. Because in kind of usual situation in physics, when you study systems which are very close to classical, it means that h bar is kind of very small number, and you try to study deviation from classical to quantum as expansion in this h bar and substitute actual value, which is for actual physical problems a very, very small number, which I don't know as a mathematician the exact value. So you consider this equations as a family of equations depending on parameter h bar. So constant became not constant. If you had oscillating integral, Yes, but it's kind of like, but I don't want to divide by I by 0, get infinity. Yeah, no, of course not. So you get a limiting point. Yeah. No, sure. Yeah, not just. But I want to say that in this integral, cannot really literally substitute h bar equal to 0. Mathematically, it makes no sense. But one can consider when h bar is very small, and what is important, if you consider any real valued function on some manifold, maybe infinite dimensional, like here we have, and to take oscillating integral as point of I divided by a very small parameter, then this integral at points when derivative of my function is not 0 the thing will cancel each other because we get like fastly rotating function, and the integral kind of average value will be 0. So the only possibility for this integral to be not equal to 0 when this derivative is equal to my function vanishes. So it means it's critical points. It's function in infinite dimensional space of trajectories. So they kind of morally the only things which contribute to oscillating path integral for a very small h bar. So you get exactly solution of Euler-Lagrange equation. And in fact, this is the origin why Euler-Lagrange equations covers everything in classical physics. Mechanics, electrodynamics, I forgot optics, which was in point of interest of Hamilton, and gravity. All classical theories are governed by Euler-Lagrange equations, and in fact, before quantum mechanics was discovered, I think people have really no clue why this Euler-Lagrange equation should cover laws of physics. And I told it's not really least action principles, it will be like really critical points for indefinite quadratic forms locally. Yeah. Okay. So yeah. So we now consider h bar as a parameter, and the integral will be concentrated near critical points, and then let's suppose they're isolated. At critical points are classical trajectories, and then we want to study asymptotic expansion of integral at h bar equal to 0 in the kind of small neighborhood of critical point. And now there is a kind of some kind of new concept appears. Usually, at least you can consider some kind of like model Lagrangian for some whatever hydrogen atom or something like this. You have some formulas for potential, and formulas are some nice expressions. So the analytic functions. So it makes sense for complex values of coordinates. It's reasonable to study not only real solutions of Euler-Lagrange equations, but complex solution of Lagrange equations. So before you have projections in Rn, when n is number of coordinates, number of degrees of freedom, but now consider passes in complex space, and you again write the same equation, and you get maybe some other solutions. So you get complexified Euler-Lagrange equation. In the formulas, you forget that everything is real except time. Yeah, and such expression contribute to so-called instanton corrections, and again, maybe in higher dimensional physics, it's also played a very major role, like instantons for gauge theory and other situations, but it also plays roles in quantum mechanics. It's also people observe it very, very early, that you get kind of this mysterious, not really physical complex trajectories contribute to some correction terms which you can see just for usual trajectories. And when you do this asymptotic expansion as a critical point, you don't really care about real numbers. There is some standard way how to do it, at least in finite dimensional case. We get function several variables, take exponent of this function, divide by small parameter. At critical points, you imagine you have non-zero, kind of non-degenerate second derivative. And there are some formal rules called weak rules. You do form power series expansion of a function and calculate something. You don't worry about whether the integral convergent or not. You produce some asymptotic series. So it's kind of algebraic notion in terms of form power series, and it works over complex numbers. And from this perspective, to write asymptotic expansion, you should forget about real numbers at all. So we consider holomorphic functions, function of complex variables. Lagrangian q and q dot will be complex variables, p will be complex variables. so Lagrangian and Hamiltonian will be complex valued functions of time. Still, time is real. Yeah, so time will be a real number between t0 and t1, and all my Hamiltonian Lagrange will be, it does make sense to be holomorphic, and real values will be like C infinity functions. Oops. Oh. Oh, okay. Yeah. Yeah, when you do this, when you try to develop this perturbation theory near critical points, you unavoidably let certain ambiguities, because what you see is classical Lagrangian. It's only kind of like leading term in H bar, and maybe there are some further corrections. Again, one have to keep this perspective. With quantum mechanics, it's like one-dimensional quantum field series. And in high-dimensional quantum field series, there's a whole science called renormalization. When you try to take perturbation theory, you get some certain divergent integrals, and then analyze them, and there are different rules how to associate finite value to integrals depending on small parameter. Yeah, so there's a whole story, and in one dimension there's no problem with normalization, but still it's kind of like very cumbersome way to do calculations. And the question, what mathematically is necessary to give unambiguous value of perturbative expansion at all maybe complex value trajectory in first order formalism. Yeah, so I forget about original Hamiltonian. I think works in this first order formalism. So my Hamiltonians, I repeat, it's holomorphic in complex coordinate and complex symplectic manifold, and maybe C infinity in time. And boundary conditions are two holomorphic Lagrangian submanifolds. And kind of couple of years ago, with Jan Sobelman, we thought about this question and developed some way to see it. In fact, it's almost tautological for people who know what is quantum mechanics. So we have a paper about a year ago, and there's a whole section devoted to this formulation. So in order to have a well-defined asymptotic expansion, complex critical points, it's sufficient to have two data. I will explain them on the next slide. Instead of Lagrangian manifolds, L0 and L, which are holomorphic, well, one should choose I will explain next slide, formal wave functions. It's sort of an analytic expression related to L0 and L, and not unique one. So there's really, from this perspective, there's no canonical way to go from classical picture to complex picture. You have to make some choices. And Hamiltonian also for Hamiltonian you also make some choice. It will be series in H bar, and the constant term, when coefficients of H bar to power 0, will be the Hamiltonian of which you started with. But then you can add kind of arbitrary terms in H bar. And to make sense as a quantum Hamiltonian, I use in a second what is called star product. Yeah. So there are choices both on boundary conditions and on Hamiltonian. And in real life examples, these wave functions are what's called WKB solutions of holonomic system of differential equations. What does it mean? Typically you get yeah, I will kind of decipher what I wrote here. I get polynomials of polynomials of polynomials. I get polynomials in variables q with coefficients polynomials in h du dq with coefficients in polynomials h bar. Yeah, because variables, things are not commuting, I have to put some order. So it's some finite expression, some power of h bar, non-negative power of bar, not power of h du dq, and some variable q. So it get like polynomial differential operators, and if you have many degrees of freedom, you should have finite n degrees of freedom, should find n commuting operators. It's called integrable system, quantum integrable system. And then for this quantum integrable system, when you try to study what are solutions, it will be, they have some asymptotic expansion, which are exponent to 1 over h bar times some function. It's called double AKB solution. And for Hamiltonian, usually, again, in kind of simple, typical models in like from textbooks, you get usually polynomial expression in these differential operators as well, and depending on time, if you have some external force. Well, of course, you can make some rational functions, algebraic functions, but some kind of explicit formulas. Yeah, what are formal? Yeah, so there are two notions: this formal wave functions and star product, which now I have to explain. Oops, it's not really. I hope I will succeed. Okay, yeah. I'll work just in coordinate space. Yeah, just before going on, I want to say that the whole story looks like I work in coordinate space, and usually in mathematics one wants to speak about like manifolds, so define things independent on choice of coordinates, and this is pretty involved picture for this all notions. It's for wave functions and star product. Better to stay in coordinate space, and it's already interesting in this situation. So consider standard coordinate space, 2n dimension with coordinates pi and qi. What is a star product? Yeah, I'll say this a little bit scientifically. You get it's a product on series of on series in bar with coefficients and holomorphic functions, and it's a product on a sheaf. What means that it's I can choose any small open domain or small ball, and the product will be defined only locally. I consider only functions defined on a small ball, and the product will be this on a small ball, and it's given by function by formulas which really depends on a kind of only Taylor coefficients of functions at a given point. So it will be associative product. It will be non-commutative product. And it's given by the following beautiful formula. It's called Moyal-Stahl product in coordinate space. What you do, you take sum over n from 0 to infinity. You consider h bar to power n divided by n factorial. And now you make certain operation for two functions, producing another function. Yeah, I didn't write it in explicit form. It starts with the usual product, f times g. The next things will be what's called Poisson bracket, and then will be things depending on high derivative. But in compact form, this formula is very nice. You take two functions of 2n variables. Consider function of 4n variables. Like you separate the first 2n variables, it's a first group, and second 2n variables, the second group. You get kind of like external product of two functions. You multiply values of functions to different points. So you get function on something of dimension divisible by 4n, and now apply B differential operator, which is written here. It's kind of alternating sum of d of pi and d of qi. You apply it n times, and then restrict to the diagonal. And this is associative product. It's very close to rules how you multiply polynomial differential operators, if you think a little bit. Yeah, so, but this Mayal product, it's very nice. It's invariant under, of course, it's invariant under translation, but also it's invariant at the action of symplectic group. Symplectic group, it's a group of preserving this two form, linear operators preserving two form. It's not the whole group of symplectomorphism, but it's sufficiently big. Yeah, so we have this invariance. And again, if you have Lagrangian subvariety in holomorphic Lagrangian subvariety in the coordinate space, then you get a module, or more precisely, sheaf of modules, because sheaf, it means you can consider things only on very small pieces of your variety, of wave functions. And there are two sheaves, left and right wave functions, which will be module over this algebra function with respect to this Mayal product. And there's a kind of very simple situation when you can kind of general case when you can describe this object easily. Namely, if you have a graph of the differential of some, if your Lagrangian manifold, suppose it projects to first to coordinates q, kind of locally 1 to 1. It's a typical situation because Lagrangian manifold has middle dimension, and you project to q, it also has the same number dimensions, so it should be typically, it is locally 1 to 1 correspondence. And the condition that the manifold is Lagrangian means that it's a graph of differential functions. So it's, there is some function of variables q, and a Lagrangian submanifold is given by equations pi is derivative with respect to variable qi of this function of q. So it's abstractly it's a graph of differential. And this module consists of the following expression. You take first exponent of 1 over h bar of this function, and h bar considers kind of formal variable. You make form power series expansion. It makes no sense because you make expansion positive powers bar, but here it goes in negative powers bar. But you just keep it exponent on the side, and you multiply by series in h bar with coefficients are holomorphic functions on q. And to be more absolutely pedantical, one should multiply by kind of factor which says how these things change if you make affine transformation. You take kind of volume complex, standard complex volume element to take square root of them. You can ignore this part. It's called half densities. And in this, on such expression, if you ignore these half densities, you can apply operator h d over dq, because if you apply these things, it will have the same form. And h over dq applied to exponent brings certain term how it acts, and one can analyze these things, and you get a module. Yeah. So what is the rough philosophy? This Mayal star product, it's like it's something similar to polynomial differential operators. Polynomial differential operators act on the space of polynomials, and they have roughly size of tensor square of the space, so it looks like space of all operators in the space of functions in Q. And but to make it kind of very good sense, it's you consider not space of functions, but functions somehow attached to this Lagrangian subvariety L. Now, this whole picture is defined when you have good projection, but if you to Q variables. But if you don't have projection to Q variables, what you do? You apply a little rotation in the symplectic group. So if projection is not submersion, you can act by this affine symplectic group, symplectic transformations and shifts. Formally on this guys, it's what's called formal Weil representations, and you put this Lagrangian in a good position with respect to Q coordinates, and you get a definition. And the theorem, it doesn't depend on the choice of good projection. So there is a lot of kind of formal rules here, which allows you to define this module as, of an algebra, like representation of algebra, associated to any Lagrangian submanifold. Yeah, so I was in this stuff about boundary condition. I said we have left and right wave functions. Oops. Yeah. I think it's stuck. Okay. Okay. It's now going wrong. Just a second, I want to check if they have. Okay. Yeah, so this is now how to. No, I explained what data is needed to construct perturbation theory in H-bar, but I didn't explain you how. And the idea is the following. First, suppose we have, when we get this quantum Hamiltonian, setting h bar equal to 0, get classical Hamiltonian. And now consider general, maybe time-dependent situation. So you have family of classical Hamiltonian. Then they define kind of Hamiltonian flaw. This p dot is dh bar over dh over dq, and q dot is minus dh over dp. You get this Hamiltonian flaw, but depending on time, you get non-autonomous flaw. And when you get a non-autonomous flaw on some manifold, if you get any submanifold, you can kind of like transport with the flaw this manifold. And so you start with manifold L0 and apply this flaw depending on time, and it will move in your ambient symplectic manifold, and you get family of Lagrange manifolds depending on time. Of course, this flaw could be divergence finite time. It's maybe not everywhere defined, but at least in some open domain, you get family of Lagrange manifolds, and they will be holomorphic because my vector fields are holomorphic, submanifold is holomorphic, so I get family of holomorphic manifolds. And now at time t1, I get a new holomorphic Lagrangian manifold, and it's intersecting with L1 exactly a complex solution of Euler Lagrange equation. It's just reformulation of the whole story. So the classical Hamiltonian moves boundary condition for the t0 to time t1, and then it's not coincide with the boundary condition t1, and consider common points. And an easy observation is that if you promote your classical Hamiltonian to quantum one, then you can transport elements of modules of formal wave functions for moving family of Lagrangian manifolds. What you do, you write kind of Schrödinger equation. What is Schrödinger equation? You have kind of like vector in Hilbert space, you get operator, and you consider maybe operator depending on time, and say that you start to move your vector such as the speed is operator applied to this vector. And this again, for this formal wave functions makes perfect sense. It's a unique sense, and you have a procedure which you can incorporate. I don't know, in computer algebra. It's really maybe a little bit of analysis because I have dependence on time, but it's something completely well defined and kind of formal and doesn't depend on reality condition, makes sense for complex things. Yeah. So what happens with this procedure when we move with respect to time our initial wave function? We get wave function for time t1. Yeah, I told you to have notion of left and right wave functions. In algebra, it's called left and right module. And in terms of formulas, replace h bar by minus h bar in star product. Yeah, so what goes on? At the end of the day, you get two, let's say, transversely intersecting holomorphic Lagrangian manifolds and wave functions, left wave function sitting on one, right wave function sitting on another. And then one can define notion of pairing, like one is vector on one space and another vector on dual space. And the pairing will be series in h bar, maybe starting from h bar to multiply by h bar to half of number of degrees of freedom. And it's usual, also usual formal weak formalism. Essentially, it's reduced to integration of exponent of quadratic expression plus higher order terms expressions. Yeah, so it's again completely formal game, and that's how we get a definition of this. How to the definition of expansion when we make these choices of initial condition, finite left condition, right condition, and Hamiltonians. And something which, again, one can try in a simple situation to calculate on computer and step by step, but it will be extremely time-consuming, but theoretically such thing exists. Yeah, now I'll give you explicit and extremely ugly example. Yeah, so it has nothing to do with usual physics at all. So forget about Hilbert spaces, real numbers, positivity, anything. But still, this is something which can produce formal expressions which will be more or less have some meanings of expansion of certain integrals. Now, for example, you can use as a left wave functions, what's called bra, cat, bra vector, like Airy function solution of Airy equation of actually will appear in maybe one of next slides of x multiplied by h bar to minus 1/3. And now, like a ChatGPT, it's no physics. Forget about geometry. I see 1, 3, and like yeah, it's completely idiotic example. I start to continue other things with like odd numbers, for example. Yeah, it's really a completely ad hoc example. I take like psi1 will be exponent to x5 to h bar, and Hamiltonian will be y to 7, x to 9, h bar to x11. Yeah, so it's kind of like large language model will produce you, if it's very crazy, such expressions. So it has nothing to do with physics. It's kind of expressions we can write. Yeah, nothing else. It's including some special functions or whatever. Yeah. Yeah, so you get, for example, these things which has no meaning in physics. There's no way to define Hilbert space operators and so on. But still, what I claim is that if you analyze from point of view of kind of physics, we calculate something which should have meaning of the following things. You take this Airy function. Okay, we can imagine if x is real, h bar is real, some actual well-defined function, but in general it's kind of maybe multi-valued and so on. Then apply to this exponent of differential operator. Differential operator, you just replace y by h bar over du dx. You get some idiotic differential operator depending on h bar. It doesn't act on any good global space of functions. It doesn't make sense what is exponent of this, but you imagine that if it will be acting on something. You get some another function, multiply by another function, which will be on the right condition, and then take the integral. In some rare circumstances, these things make sense, but we want to make asymptotic expansion of things which do not make sense. And the conjecture, which one can try to check on computer, because I said this whole thing can be, in principle, one can calculate on computer this asymptotic expansions. It's kind of using computer algebra, and it will be a very long calculation for producing some series. Oh, sorry, it is a misprint. You get some expansion, sum of Cn h bar to power n, and these expressions are divergent. but the conjecture is that they're what's called resurgent. It's a good divergent series from which one can make sense of their sum. Namely, the nth coefficients for convergence series should grow exponentially, but here it grows faster than exponential. You have factorial factor here. So it should grow really like factorial times some constant. And what does it mean, resurgence? If you get 4 power series with factorial growth, you can try to make series which is convergent. You divide by the factorial. And you consider sum of Cn over n factorial some z to n. Z is some, it's called Borel coordinate in Borel plane. It's some another variable. It's not h bar, but kind of like dual variable. And you get a germ of analytic function in what's called Borel plane. And the property of binary resurgence roughly means that you get this function, and it should be defined almost everywhere. Maybe it should be multi-valued. So if you consider generic path starting from 0, then it will have analytic interrelation along the path. So it will be some singularities, locally will be isolated singularities, but if your path avoids the singularities, then you have an endless analytic continuation. So there are functions which don't have endless continuation. There are plenty of analytic functions, for example, they can be defined only in unit disk, and there's no way to go outside, like modular forms. Modular forms really defined on unit disk, but this endless analytic continuation, it's kind of like analogs of algebraic functions in word of in analytic theory. And let me give you kind of definition of a very typical situation with this resurgent function. One can be a bit more precise. It's called simple resurgent package. So we have maybe countably many complex numbers, and for each complex number, you get 4 power series in one variable, in a variable h bar, again with this factorial growth. And also you get, for any two these pairs of numbers which are distinct, because numbers can be repeated in this list, you have something called Stokes index, some integer number. So the whole this data, and the property is the following. For each number, the alpha, you consider analytic function defined near point the alpha by dividing by factorials and shifting one variable in Borel plane. So you get a function near for each point, you get function near this point, and then start to make analytic continuation, and then if you consider any path avoiding this other singularities, we'll have analytic continuation, and when I approach other singularities, what happens, I'll get functions without singularities, holomorphic function near another point, and plus some integer coefficients, more or less this Stokes index, multiplied by log of a logarithm of local coordinate, z minus zb, singularity, times the function which exists at another point z beta. Okay. So the integer coefficients depends on the path, and what's n alpha beta, it appears in the following way. You can go from point z alpha in straight direction to in complex plane. If on this ray sometimes on this ray you can meet other singularities, and you should have and now you say avoid this when approach this other singularity, you just avoid a little bit on the right. It's just convention. And then for this path, when you do the structure of singularity near point z beta, you get this integer multiplicity towards n alpha beta. So you get some integer numbers. And then if you go on the continuation of path which doesn't pass through the other point, you can go forever, and then you go to some extend to your function to some star-shaped domains. You make some discrete collection of paths. So it means that for each point, you make this maybe infinitely many cuts going radially from this point, and on the complement you get a well-defined function. And there is a procedure called Borel summation, assuming some integral is convergent. If you get generic direction in the complex plane, which is not Stokes ray, you will make a kind of Laplace transform of your analytic function restricted to this ray, and you get something which is holomorphic in certain small sector and has a symptotic expansion, the series which you start with. Yeah, so you will make sense of values of divergent series. It will be actual analytic function, but maybe in a sector. Yeah, so that's a picture of resurgence. Yeah, this appears in finite dimensional situation. That's the simplest case. Suppose you get finite dimensional complex manifold, you get holomorphic function, and you take a holomorphic volume element. And then you can try to integrate exponent minus function of h bar times volume element over some cycles integration such that function divided by h bar decays very fast at infinity, and you hope this integral is convergent. So you get actual integrals. And the asymptotic expansions are, for various critical points, form as this simple resurgent package. Yeah, one can analyze, first start with Gaussian integral, get only one critical point, or you can make Airy function. You get a function, this will be for you definition of Airy function. You integrate cubic polynomial, not quadratic, just in one variable, and so on. You get Bessel function. So I said that if you get, let's suppose in generic situation, critical points are holomorphic more, so second derivative is not degenerate. Then you get finitely many expansion which you can calculate algebraically at critical points, and they form simple resurgent package. And the Borel summation gives actual values of integrals of kind of steepest descent contours, which are called Lefschetz timbals in these situations. Yeah, and now I kind of go to the end. What we expect when we have resurgence in quantum mechanics? Yeah, so I explained you there is some formal procedure. If you get some formal series in h bar for wave functions for Hamiltonians, you get again new form of power series h bar coming from how you interpret expansion of this path integral. And when this guy is resurgent, so when one can try to make sense of this as actual function, not on just asymptotic expansion, definitely one needs to put some condition, because if you start with arbitrary form power series, there are too many of them. And there's no hope to be this guy to be resurgence. Resurgence is a kind of special form power series. And there's a simple definition. When you get the simple resurgence story, you can imagine that it's not just one given collection of points and expansion, but things depending on some parameters, finitely many holomorphic parameters. And you again imagine a situation like you get this exponential integral in finitely many variables, but everything starts to depend on parameter. And then Stokes constants, if you move parameters, then can be recalculated with something called whole crossing formalism. So if you know at one point of parameters, you can recalculate in any other point in parameter space. And this kind of very vague conjecture that it's under favorable circumstances, so it's not mathematics at all, it's kind of like witchcraft at the moment, that if you start with this left and right wave functions and Hamiltonians, there are some series in h bar depending on parameters, like in Q, on P in Q. If they're all parametric resurgent objects, belong to some nice family with other expansions and other critical points, then the formal expansion of path integral again will be simple resurgent. So resurgence will be reproduced for path integrals when you have input which is resurgent, and output will be resurgent. It's kind of like big project, and even to formulate in which what really. Oh, sorry. What a potential what really goes on? It's a big enterprise. So there are potential applications. Yeah, first consider solution of equations depending on small parameters, double KB solutions, which have again this form exponent of some function of h bar plus high terms. This part of the game when you get 2 Lagrangians and 0 Hamiltonian. It's this class of examples. There is another example. We consider periods of quantum integrable systems. It's a bit long story. It's in physics was developed by Andrea Voros, called Voros symbols, and it's related to another important question in quantum mechanics. When you get quantum integrable system, what will be joint spectrum of Hamiltonians, and there are some called Bohr-Sommerfeld rules, and there are some high corrections which are governed by this story. This is already it's another part. It's kind of like parametric resurgence here. Then one can do small time symmetric of heat kernel. You have random walk with very small time, and again by formal manipulation one can put it. You divide something by h bar, and it's related to some big piece of science developed by Gutzwiller, relation of spectra and lengths of geodesics for Riemannian manifold. And finally, there are things like generalized finite num sums. These things which appears in quantum Witten-Reshetikhin-Turaev invariance for closed Riemann manifolds. If you make triangulation, you get a certain expression which has roughly the following form. Here it's a simple example. You take parameter n, h bar will be take only discrete values, but still going to 0. Q will be roots of 1, very close to 1, and get the finite sum of something, depending on 2 integer parameters a and b. And it has some symptotic behavior. And then we analyze it and develop what is form power series, calculate on computer, calculate 100 terms of expansion. Yeah, so it's a very controllable situation. And then one can see all this resurgence literally. And in this particular examples with parameters a and b, my postdocs, Veronica Fantini and Campbell Wheeler, very recently rigorously established resurgence for these examples and stuff like this. And they introduce kind of very general idea that if you have parametric resurgence, then you can integrate your own parameters. And again, resurgent functions. And sometimes you can really rigorously prove it. And for such situation, one get control because it's reduced to some finite dimensional integral. And then something called Fadeev quantum diallogarithm, which is not given by some finite dimensional integral, but for which we know resurgent properties, and the whole machinery works. And so at least we have first working examples when all this project gives some actual fruits and actual theorems. Okay, thank you.
Thank you. Questions, please? Yes?
From physicist perspective, so when we do, let's say in quantum field theory, when we Borel transform asymptotic perturbative series, typically we get singularities and then Laplace integral. Sure, we can go around the singularity, but it's regularization dependent, so to speak.
Yeah.
So it looks like you have cases in which those dependencies disappear, or
no. You get the same problems, but at least what I claim, I get kind of rigorous calculation scheme which can implement on computer and maybe eventually actually calculate this Borel transform and get actual numbers.
That would include all the
yes.
Thank you.
Yeah. Okay.
Thank you. In this Reshetikhin-Turaev story, do you expect like finitely or infinitely many of those singular points, and what do they mean?
No, we have a complete picture. We have finitely many series because what happens, you consider like critical points of finite linear combination of dilogarithms and squares of logarithms, and if you write equation of critical points, you get actual algebraic equations called num equations. You get typically finite many solutions. But And here there's some kind of a little bit stupid redundancy. In actual integral, each critical point appears infinitely many times because to logarithm at integer multiples of 2 pi I squared, but this thing gives the same series. So you get only finitely many series, but infinitely many stock constants because actual values can shift by integers.
But do you expect the relation to topology of your manifold or topology or those
yeah,
points?
but in fact one can this finite num sums, it's kind of very general class of expressions which can write sums of maybe many variables. They include all manifolds. One can analyze how to relate to 3 manifolds, but I think it's better to study its object by itself without forgetting about manifold. Yeah.
Okay, thank you.
Thank you.
Oh, yeah?
I have a question. So your analysis was based on semi-classical expansion, meaning Planck constant goes to 0.
Yeah, yes.
So imagine I take this example which you have shown, and I just look at this as a function of Planck constant and going to the limit when Planck constant goes to infinity, just opposite limit.
Oh, that I don't know, yeah.
But assume this limit exists. Then you're going to get some nice function of h bar.
Yeah, no, usually, but with the function of h bar, it's got many functions because it will be one function, one sector, another function of another sector.
My question is exactly this one, that imagine I give you a function such that for large h bar, it's well-defined nice function.
Yeah.
And for small h bar, it has these barrel singularities resurgence issue. And at the end of the day, by providing prescription, you're supposed to construct a function such that it will interpolate behavior on both ends.
Yeah.
And you get a smooth translation from h bar to small h, where all these problems have to be resolved in a certain way.
Yeah. No, in fact, there is such situation that sometimes one can analyze and when h bars go to infinity. It's called exact WKB method. For some polynomial operators, in, let's say, in one variable depending in h bar, in a nice way, one can calculate this what everything was you want, maybe this Voros symbols, by very effective procedure because it's like you knowing behavior of function everywhere on complex plane, like you reconstruct rational functions from poles at all points, including infinity. Yes, there is. One can translate it sometimes to effective procedure. This extra knowledge is h bar goes to infinity too.
But my question is more practical. Practical in the sense that as a physicist, imagine I want to compute whatever something in quantum mechanics for exact value of h bar, knowing that for h bar to 0 there is the resurgence, and for h bar large, it's well-defined function. So what will be the prescription to interpolate between the two regimes? What shall I do?
Yeah, no, you do some kind of a Riemann-Hilbert problem. You can, I don't have a general answer, I have to say, yeah.